Namaskar, welcome back. So this was the last slide uh, uh, where we stopped and we were talking about the passage of uh, the S waves. Okay, and this is typical of that, which was because of 1999 Chichi earthquake of Taiwan. So this was also observed and during the 2001 Bhuj earthquake, and this is on the there's a bridge which connects the southern portion of Gujarat with Kutch. Okay, so that also got waved up, and this is exactly the similar example what we were looking at in of Chichi earthquake of 1999. So this was the bridge. Of course, the surface on which the bridge has been constructed must have been waved up similarly. Okay, and this is what we saw in the ground, the epicentral area where the whole uh, the agricultural field was waved up as the wave passed through this area. Now coming to the rest two waves which have been left out and which are broadly under the category of your surface wave, and these are the low wave and your relay wave. Okay, so the low wave uh, results into again the direction of propagation is in this direction, and then you have uh, the the movement or the motion of the it will be something like it will horizontally push and pull the ground. Okay, so and then you have the relay wave. So this one usually you what you see is that it moves the ground in horizontally in this direction, and then direction which almost like propagation is perpendicular to that. Okay, and the relay wave will be something like it will move ground up and down. Okay, but in an elliptical fashion. Okay, so now you can think of that all sorts of motions are going to be experienced during the major earthquake. Okay. So this is what you will see in terms of the surface waves and relay waves. Okay. Oh, sorry, surface wave, which is your low wave on the top. This is your low wave, and this is your relay wave. So in this, you may face this type of situations if you are having two buildings which are constructed closer to one another. So if you look at what we were looking at the body waves, okay, that it will partially damage the structures, but this can result into the total damage. Okay, so S waves are more dangerous and all that, and we will also learn about the waves in terms of the frequency. We will also talk at the end, and what is the importance of that. Okay, so this is in concise in a tabular form we have given the seismic waves, body wave and surface wave, and motion and their names. Okay, so P waves are also termed as longitudinal waves, then transverse waves, horizontal transverse, and vertical elliptical. Now coming to the part that is earthquake, and as we have been discussing about that what exactly earthquake means. Okay, so what are earthquakes or what is earthquake process we are talking about? So the energy which has been stored because of ongoing deformation caused by plate tectonic uh, movements or plate movements, either they are subducting, colliding, or passing by past each other, but overall there is some energy which has been getting stored. Okay, that is in, we can say the strain is getting accumulated, and sudden release of this energy is your earthquake process. Okay, and one can see or, uh, or the manifestation can be seen on the surface as it has been shown in this photograph. This is a photograph of San Andreas fault system, and this line which you see, the straight line groove like feature on the surface, is nothing because but it is the what we call active faults. Okay, so these are been termed as active faults, just and they they have a very typical motion or sense of movement. So these are what we call active faults. So we'll slowly learn this also, that how to identify this signatures of past earthquake on surface, and also we'll try to look at that how we will identify the signatures of past earthquake preserved in sediment succession. Okay. So another photograph of the San Andreas fault system, where you see here that these are the streams which are offset or offsetted because of the movement. Okay, and the movement has been shown by uh, these arrows here. So this portion of the fault is moving like this, and this portion is moving like in this direction. Okay, so you have the sense of movement which you will learn, and different type of sense of movements are there, different in different settings in terms of the plate deformation. So that also will learn. There is very good example which has been given by USGS, explaining how you can just experience uh, that if what happens when a sudden energy has been released. So there's an example which has been given, that you just try to push uh, your arms and then try to release it. Okay, so you will feel a sort of a jerk on your arms. Okay, and that is exactly what is happening when there is a fracturing of the crust because of the sudden release of the stored energy. Then another part which is important here and was been pointed out in many of the textbooks and the many scientific uh, groups, they have emphasized about that with when there is such type of deformation, then it is not only that for along one weak zone it will be released, or the energy which has been stored will be get released along the one single weak zone. There will be multiple weak zones which exist. That is what we call the cracks, or in a simple layman language, but these are all faults, because there is a movement along this. So it will get released along different fault lines. Okay, this what we termed as a fault lines. Okay, and since they are capable of triggering earthquake, and the earthquakes have happened in the past, then we call this as an active fault lines. Okay, so this is from San Andreas fault system, where you have multiple faults here. Okay, so this is these lines have been shown here. There are multiple faults. Okay, and then they have given also the numbers here, which are the rates. Okay, that is in millimeter. It talks about. Okay. So now you can recall the part which we were discussing, and we had a discussion during uh, the plate tectonics just after that part about the Indian plate. Okay, and we discussed there that the if you remember this. Okay, so we were talking about that we have the Indian plate is moving towards the Eurasian plate or Tibetan plate. Okay, so this is your Indian plate. So that is moving at around like 50 millimeter per year. Okay, and then we also had discussion that across Himalaya it is consuming around 20 millimeter per year, and rest till the Himalayan part. Okay, what we say, it is around 5 millimeter per year. Now this 20 millimeter is not just been released or getting been released along one single fault line. Okay, so it has been consumed, we can say. So it has not been really, or this has not been consumed by one single fault line. Okay, it gets distributed along multiple fault lines, and that what we also had discussion that in Himalaya, if you take, we have multiple weak zones, and that what we call Himalayan frontal thrust, then we call main boundary thrust, and then you have main central thrust. Okay. So this is the present day boundary between your Indian plate and Eurasian plate, or you can say Tibetan plate. So this different fault zones are consuming your this 20 millimeter across this. Okay. So similarly, in this region, what you see is that you have different slip rate, and that slip is having a direct relation with your accumulation of strain. Okay. So the portion of the weak zone or the fault within the fault system, if you have, wherever we see a higher uh, accumulation, or we can say the slip of the fault, okay, that area is more vulnerable and can produce earthquakes in a very shorter interval. Okay. So we can say that more the the slip, okay, shorter will be earthquake interval, and this goes similarly opposite. Okay. So this is also important to have an understanding. So what we usually do, that part we will also discuss when we are coming to these topics in detail. But here we use like GPS measurements, which will give us that. So GPS measurements will give us short-term deformation, and geological, we can also say geomorphological. Now this studies or finding will give us long term. So usually what we do is we try to combine these two and then correlate with each other and try to see that what we see now was there in the past or not. Okay. So GPS, no, so these are the based on all like GPS estimation, uh, and if we consider that this part here, that is more the slip, so this area is going to trigger more earthquakes in shorter interval, and whereas this one will require longer time span to uh, trigger an earthquake over here, because all material within the interior of earth, or we can say the crust, will have different threshold limits. Okay. And to fracture that, definitely you need a certain amount of energy stored. Okay. Now as we were discussing about this, that if you take this the fault lines here, okay, then this fault lines are not slipping at the same rate, they are slipping at different rate. Okay. So to understand that, the easiest and the best way, which is again explained by the USGS, that you take the set of playing cards and try to move while pressing it. Okay. So the boundary between each card is your fault line, and so that you will understand that all cards are not going to move at the same rate. Okay. The outer ones will move faster, but the inner ones will definitely will have some sort of a slower slip. So that depends again that in what which direction the slip or the movement of the plate is. Okay. That is also with respect to the other plate. So this is an again what we see, and they have explained this and tried to compare this with the deformation going on between the Pacific plate and the North American plate. So, deformation of rock under tectonic stresses, usually the rocks, as I told, that they has, or the material of in the crust will have their own threshold limit, and but it goes through a process of elastic deformation, ductile deformation, fracturing finally. So, this fracturing is your, what we call, is your earthquake. Okay, so this is going to be your earthquake here finally, but not all rocks, okay, or the material are going to get deformed elastically. Some, yes, of course, because it depends on that at what which location in terms of the depth the material is. Okay, so again, if you, so that was also the previous one also was the stress strain diagram, and if you take this one here is more or less what same we are talking about. Okay, so we have the elastic deformation which is reversible, and we see this at the time of or after the post deformation. Okay, because material in crust is elastic. Okay, so they will have what we call the theory of elastic rebound. So that part is also been seen, which is the energy is reversible, but not complete deformation is gets reversed. Okay, that is, if you have the slip of around 10 meters, then you cannot say that all 10 meters will come down. There will be some sort of a residual which has been left out. Okay, then you have non-reversible, that is plastic deformation, and finally fracturing, that is a brittle deformation. So with increasing stress, a rock deforms elastically initially, and this part, okay, can be captured by GPS, present ongoing deformation, because this is going to be a very slow process. Okay, because for triggering an earthquake it may require an interval of almost like 600 years or 400 years, or it goes up to like more than 2000 years also. Okay, so initially the rock deforms elastically, then plastically you are having, then and before ultimate failing or breaking in an earthquake. Okay, that means you are having elastic, plastic, and final you will see a sort of a brittle deformation. Okay, brittle failure. Okay. So, and that is your, what we, it says that a completely brittle rock fails at its elastic limit. So it has a threshold limit. Okay, all material will have threshold limits, and that after that it will definitely break. Okay, now as I was talking about the conditions what you are having. Okay, whether it is the material has been sitting in the deeper portion of the crust or it is at the shallower one, so that will also affect the pattern of deformation. Now this is an example which has been shown of a cylindrical block of marble. Okay, so under condition representative of shallow crust. Okay, so we are not going deeper, because deeper you will have higher temperature and pressure. Okay, so the shallower part, if you see, then you will experience, or you will go through brittle deformation. Okay. But in case of your deeper crust, okay, it will result into, like, it will act as a ductile deformation. It will not be brittle. Okay. So, so no major fracturing will be seen during that type of deformation. Okay. So one has to be very clear that where we are actually at the deeper or we are at the shallower. And deformation will also be directional. In the deeper portion, you will see an uniform stress are acting, but on close to the surface, you will see a directional deformation. Okay, where sigma 1, sigma 2, sigma 3 is what we were calling, like we consider as a minimum, intermediate, and maximum one. Okay, so the sigma 1 will help, or maybe you can say that it will govern the orientation of the material within the under the deformational condition. Okay. So, for example, if you take that development of different textures in rocks, they are also indicative of the uh, direction of different stress conditions. Okay. So, for example, you have granite here, which doesn't show at present like preferred orientation of the material or the minerals, but later when it has been put under like a unidirectional stress, then you will see that there is a clear cut alignment or the orientation of major and minor minerals. Okay. And the granite change over to granite gneiss. Okay, this is a typical texture of that. But the result is because of the high temperature or high stress in from sigma 1 from that direction. Okay. So, this is can also be seen in most of the examples that how the stress pattern changes and it results into different type of deformation in the area. Okay. Now, earthquake forecasting and prediction. Now, this is very exciting topic in the sense because most of us are interested in that how we can forecast the earthquake, how can we can predict the earthquake and all that. Okay. Forecasting till date is not so like we can say explicitly successful, but yes, to some extent people have tried in many other countries and they got success for like few, very few, but still people have been trying, the scientific groups have been trying to have some sort of, and forecasting can be done and prediction can be done. Okay. Now, forecasting basically identifies both earthquakes, then prone areas and man-made structures that are specially vulnerable to damage from shaking, that is your seismic shaking. So, mostly we are worried about that which are the areas which are vulnerable and the seismic shaking, what will happen, okay, to the man-made structures. So, this is very common uh, uh, like reason to have the detailed understanding of this. Okay. So, unless and until you are not having proper identification of the prone areas, you won't be able to do a proper hazard assessment in that region. Okay. Now, earthquake prediction refers to attempt to estimate precisely, but there is a big question whether we can do that precisely or not. When the next earthquake, the question always remains when the next. Okay. So, when the next earthquake on a particular fault is likely to occur. So, this question always remains that how we are going to predict and when it is going to happen, where, so that area is also important for us. Okay. And then how many houses which are being constructed, whether they will be able to sustain uh, the ground shaking or not. Okay. Now, earthquake forecasting is based largely on elastic rebound theory and plate tectonics. The elastic rebound theory suggests that if fault surface do not slip easily past one another, the energy will be stored in elastically deformed rocks. Okay. Just as a steel spring that is compressed. Okay. So, you just keep that energy stored, but it will be released at one point of time. So, currently seismologists are using GPS, okay, to measure or monitor the accumulation of strain in rocks near fault lines. Okay. So, before your, like for example, if you take a layer here and you keep deforming, okay, you are having this stress here. Okay, you can either say sigma 1 is there. Okay, fine, then it will keep start deforming. Okay. Now, this deformation is what we are talking about, the related to your elastic rebound theory. Okay. So, finally, you are having this deformation ongoing, which can be measured if you are having GPS here. Like for example, you are putting a GPS here and you are having GPS here. So this will keep deforming, okay. And maybe one you can have here. So there are multiple things. Now finally it will fracture, okay. So finally what you will see is that there it has been fractured. So this displacement along this will be your earthquake, okay. So you need to have the understanding of the active fault, and slowly we'll move to this topic. So I'll stop here, and we'll meet in the next lecture where we'll discuss more about the hazard related part and what is the role of the seismic waves, the epicenter, how we can identify the epicenter and all that, okay. So till then, thank you so much. Namaskar.